Okay, and Michal, please continue.
Okay, so welcome back. I got a question that my Lagrangian is not really augmented Lagrangian. that's true, but if so, I have a general penalty function there, and with a proper choice of that penalty function, I can actually redefine the standard augmented Lagrangian method. So it depends on the penalty function, but whatever you call it, Lagrangian, generalized Lagrangian, modified Lagrangian. Okay, so before I go to the other examples, I still would like to present 3 slides about PenLab, because that's my favorite example, just to show that using that general code, you can solve different kind of problems in one shot using one algorithm, using one code. This is kind of artificial example of robust quadratic programming on unit simplex, and I don't have an application for that, so take it as an academic example. Okay, I have a quadratic program on Unix simplex, and what I assume is that that my matrix A is uncertain, but not in the sense which you would find in other papers. Well, Bental-Jemirovsky would tell you, okay, the matrix is uncertain, which means that every element of the matrix is uncertain. Every element of the matrix lie in some, let's say, ellipsoid. I assume that the whole matrix lie in an ellipsoid. That, okay, if it's a huge matrix, and there are some relations of the element of the matrix, so why to allow each of the elements? Let's allow the whole matrix to move within some ball, and the ball is defined as a spectral ball. So A0, the center of the ball, plus some epsilon times a matrix which is symmetric, and the spectral norm of the matrix is smaller than 1. This is in fact a trivial problem, because if you define the robust counterpart, what is it? We minimize the quadratic function, but we minimize the worst case quadratic function. The maximum is taken over all the matrices from that uncertainty set, subject to the original constraints. And it's easy to see that you can solve that directly, the maximization problem. The optimum will be attained either with A0 plus epsilon identity or minus epsilon identity. So you can plug in directly the optimal value for this maximization problem into the minimization problem, the outer minimization problem. And okay, this is a QP. Well, you solve that QP, it's a robust counterpart. The trick here is that I don't want to consider any optimum. So, well, okay, let's say we solve the robust counterpart. We will get an optimal solution, X star. We will get an optimal solution, A star, which is A0 plus epsilon times some U star, which may be plus minus identity. It may be some other matrix. The optimum is not unique. But now assume that the matrix A star, the optimal matrix of the robust counterpart, it should share some properties with the original matrix A0. For instance, if this was a stiffness matrix coming from finite element discretization, I know that the sum of the rows is always 0 of the stiffness matrix. I also want this robust counterpart. It may be some perturbed matrix, but it still may be required to be a finite element matrix or stiffness matrix, perhaps for some other mesh, for some other problems, but it's still a stiffness matrix, so it also should have the sum row equal to 0, which will not be the case with the optimum we computed. Or I may require that the diagonal element, that the matrix is okay, that the diagonal elements of the original matrix were equal to 1. I still require it to be equal to 1, which means that the optimal matrix U should have zeros on the diagonal, again, which is not the case of the identity matrix, which I computed there. So once we add this constraint that actually the perturbed matrix should satisfy some more constraints, this equivalence is no longer true, that we can solve that directly. And okay, what can we do? Well, we can, again, it's an academic problem, so just a proposal. What we can do, we can take the given X star and we can find a feasible matrix A hat, which is feasible in this in this new constraint. A feasible matrix for the maximization problem. And that's a linear SDP. So we solve that's the maximization problem from the robust counterpart. That's the original constraint. But now we have this additional constraint, for instance, that the diagonal elements should stay the same as in the original matrix. So we can solve that linear SDP, or if you like, we can solve a nonlinear SDP, just trying to find, so we have that given matrix, we compute it, A star, and we try to find a feasible matrix with that new constraint, which is as close as possible to that in the least square sense, for instance. So it's your choice, linear or nonlinear SDP. So we will get a matrix A hat, which is a perturbed matrix, let's say the worst case matrix, but feasible with the new constraint. And okay, finally we need to get the solution of the QP with the new matrix. So we have to solve one more QP with that new matrix. So altogether we have to solve four problems: the original, the nominal QP, the robust QP with identity matrix here, the linear or nonlinear SDP to get the feasible matrix for the robust counterpart, and finally the QP with that feasible matrix. And that all can be just done using PenLab, using simple commands, because this is QP, 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 QP on a unit simplex, so you can predefine a module for QP with a unit simplex. And okay, so here's the sequence of codes of commands when we solved it. So we solve different QPs on the top, then another QP with a different matrix. Here is the preparation and the solution of the linear SDP, and in the end I solve another QP now with the new matrix. And so if I run all that for, I think I have a random matrix 9 by 9, so random problem. If I solve it, so you don't see, okay, yeah. So you see, this is the result, which I didn't define a path for the code. So this is the result you would get: the optimal value of the nominal QP, the optimal value of that robust counterpart, but infeasible, which is worse. It's the worst case robust scenario, and the feasible robust, which is better than that, because the uncertainty set is smaller, but it's worse than that because the uncertainty set is something still. Okay, so that was the final illustration of how easy you can program things with PenLab. So I can close that. So now let's go to polynomial optimization, because that's a conference on polynomial optimization. So this is an application where we need bilinear and higher order nonlinear SDPs. The application was done in cooperation with Didier Andréon from Toulouse, and if I say in cooperation, he actually did all the modeling, most of the work. We just provided the solver for the resulting bilinear or polynomial matrix inequalities, because I'm definitely not an expert in the control theory. So okay, it's about BMIs and PMIs in control theory, in particular in the static output feedback. So we have this standard linear system here with the data matrices A, B, C. See, those are square matrix, rectangular matrices. And what we want to do, we want to stabilize that system by output feedback. So we want to find a matrix K such that, so if we, okay, see if we find K, then we can substitute here, and we will get BKY, and we can substitute for Y. So we will get AX plus BKCX, and the resulting system matrix, which is that matrix, it should be stable in the standard sense. So all the eigenvalues should be in the left half plane. And the standard way how to solve that is we have Lyapunov stability theorem. The matrix is stable if and only if our matrix is stable if and only if there is a matrix P, which is positive definite, symmetric, and that Lyapunov product is negative definite. And so to find the stabilizer, to find the matrix K, we have to just solve this feasibility problem. And you see that's a bilinear matrix inequality, because the variables are the matrix K, which we have to find, and the Lyapunov, the auxiliary variable P. Multiply here, it's a BMI. And either we can treat that as a feasibility problem, or we can treat it as an H2 problem, where we just add some, I just skip these details, where we just add some objective function. So in the end, what we solved here was such BMI. Again, we have this Lyapunov condition here with variables K and Q. Q is positive definite, so this is bilinear, this is linear, and we have some additional linear constraint. We have linear objective. So this is the tricky part here. But we have that code for bilinear matrix inequalities. So we can solve that, and that's from an old paper with Didier. We solved a number of problems, and there are many more problems. All these problems are from the library composed by Friedman Leibfried. He calls it comp-lib or comp-lib, as you like. And those are problems of that type with different sizes, of different type. What you see are only kind of small problems, because by PenBMI we couldn't solve larger problems, because unfortunately in that library there are either small problems or very large problems of very large dimension. But even on these problems, you can see those are the original dimensions of those problems, of those matrices A, B, C. Those are matrices n by n, p by n by p, and by m. And these two numbers, those are the dimensions for the bilinear matrix problem. So those are the dimensions of the matrices given by the given to the code. And these are bigger because we have to introduce the Lyapunov variables. We have another artificial variable. So that's the trouble here, that even for smaller problems, because we consider that Lyapunov stability theorem, we have to introduce the Lyapunov variable, and we suddenly get, well, not really a large dimension, but definitely larger than here. And if we went higher with these numbers, we would get much higher with these numbers. You can see that that's the CPU time. This was computed by PenBMI, the C code, and you see that everything could be computed quite quickly. But as I mentioned, the trouble here is the Lyapunov variable. So our question was, can we avoid that auxiliary variable? Again, we have the data matrix, or the matrices, the variable matrices we have to deal with are the matrix K, which is the stabilizer. That's what we have to find. The dimension is n by p. Then the Lyapunov matrix, this auxiliary matrix Q, the dimension is n by m. And we have one more matrix p by p. And typically, always, n is bigger than p and m, and typically it may be much bigger than p and m. So that matrix is the big matrix. That's not big, so that's relatively small. So the Lyapunov variable, it dominates, but it's just an auxiliary variable, and we don't need it. We don't need any information from it when we solve the problem. We can just throw it away. There's nothing important there. So can we get rid of that? And it turns out we can if we switch to higher order polynomials, not EMI, just to higher order. How do we do that? So first let's vectorize that matrix variable. Okay, so instead of matrix m by p, we get a vector m times p. Then, now, the condition is that this matrix should be negative definite. It should be stable. Okay, so we write down the characteristic polynomial of that matrix, which is that polynomial. And it's a polynomial in variable s, but we have that parameter k. So k is our variable, and of course the polynomial, it depends on that matrix k. So we can write it in that way. So those are the coefficients of the polynomial, and the coefficients, they depend on k. And okay, that's the variable in the polynomial. Now the coefficients, they depend on k, but they're actually polynomials in k of that type. Let me show you an example. I hope it's not too small. For such a small problem, we have matrix A, B, C. But the matrix K will be, the variable is K1, K2. Now, this is my determinant of Si minus A minus BKC. Expressed, it looks like that. So it's a polynomial. That's the absolute term, linear term in S, quadratic, cubic in S. And you see the coefficients are polynomials in K. In this case, those are just linear functions in K, because the matrix here is a vector. But in general, those will be polynomials in K, the coefficients of the characteristic polynomial. Okay, and for stability, we need to guarantee that that all roots of the characteristic polynomial belong to the stability region, which is the left half plane. And for that, we have the Hermite stability criterion, which says that indeed all roots belong to a stability region. In our case, it's the left half plane. If and only if this matrix is positive definite. And what is that matrix? That's the product of the coefficients of our characteristic polynomial, qi times qj, multiplied by certain matrices. And the type of these matrices, it depends on the dimension and on our stability region. So for the particular case of the left half plane, let's say if the dimension of that problem is 3, then HQ would look, for instance, like that. Well, not for instance, so it would look like that. And you see, so that matrix, so the Hermite stability criterion says that if this matrix is positive semidefinite or positive definite, the original problem is stable. And this matrix, you see, it depends on the coefficients of the characteristic polynomial, but these coefficients, those are polynomials in K, so we get some other polynomials in K because we still multiply these coefficients. So altogether, that what we get is a polynomial matrix inequality because we get a matrix which depends polynomially on the original variable K, and it should be positive semidefinite. So we can write, or positive definite. We can write it in this way, where these would be some matrices and those would be the monomials, all possible monomials in K. So again, the lemma is that the original problem is solvable, so that K solves the original static output feedback problem if and only if vectorized K solves the polynomial matrix inequality in here. So we avoided the Lyapunov matrix, but we introduce higher level polynomials. Okay, well, we have okay, forget the color. So if for some specific cases, this would be just BMI, because when we wrote that paper, we did not know how to solve polynomial matrix inequalities. We are only able to solve BMIs at that time. But now we can solve polynomial matrix inequalities as well by Canon or by PenLab. And just when we compare the dimensions of the problem with the Lyapunov variables, if we solve the BMI using the Lyapunov theorem, the variable is m by p and n by n, and again n is the large number, while for the polynomial matrix inequality formulation we only have the variable m by p. We have seen this example already. Now to program that in PenLab is not direct, but it's sort of easy, because we have the predefined module for polynomial matrix inequalities. So you have to give your data matrices in a certain format. Then that's the predefined module which defines the polynomial matrix inequality, and then you just solve the problem. So the main trick is how to get from the data of the static output feedback from the matrices A, B, C, how to get the polynomial matrix inequality, the matrices H. And that's actually quite tricky, and that was done by Didier. So he wrote this code which takes the data directly from compiled, I don't know how you want to pronounce it, and translates it into the H matrices for the polynomial matrix inequality. But okay, that's there as well, so that's part of the predefined or part of the PenLab distribution. So now if you want to solve that static output feedback problem, you take any example from the complete library, just give it as an input, and okay, you solve it up to here, and this is just, you check if the solution is a good solution. And okay, here that's the same set of examples from the comp library, from the Friedman-Leibniz library, and you see that's the size of the problem. It's now small because we don't have the big matrix anymore there, but now we have the polynomial matrix inequality there. So this is the corresponding degree of polynomial for those particular problems. Sometimes it's just bilinear, but sometimes it goes up to degree 7 or 8, so it's not a trivial problem at all. And you can see here that's the CPU time to solve the problem. You can't really compare it with the old table, because that was a code programmed in C. This is the MATLAB code, so it will be slower. But you see that the number of iterations is reasonable, but you can also see that if the degree of the polynomial goes higher, then we do have troubles to solve the problem. The problem becomes more difficult with the higher degree of the polynomial. But still, it's solvable, and we can solve it. Okay, so that was about polynomial matrix inequalities. Now the next example of nonlinear SDP is here. It's approximation by non-negative splines. Completely different area, completely different application. Imagine you have a one-dimensional function which describes something. For instance, it describes the number of hits to a web server or to an email server. Let's say the function is defined between 0 and 1, and it's a noisy function, so there's some perturbation in the values. So what we have is just some noisy values, pi, at some points on that interval 0, 1. And we want to approximate these noisy values by a smooth function, let's say by a cubic spline. That's a standard thing from numerical analysis. So what we need to do, we need to find the coefficients. So first we need to define the interval 0, 1, some sub-intervals where we will have the knots of the spline. So on each sub-interval we will have a polynomial of degree 3, and where we glue these two polynomials, it still should be smooth enough. So we want to find the coefficients of those polynomials on these sub-intervals, and those are the conditions that it still should be smooth enough. So that's okay. It's a continuous function. It's C1 function. It's actually C2 function. Okay, so that's the standard thing. So if you want to find the closest spline, we just minimize the L2 norm between the spline and the given points of the function, subject to conditions. So we minimize with respect to the coefficients p, subject to conditions 1, 2, and 3, which were those equalities. Okay. Now, let's assume that we have another condition, that the function f is non-negative. So we also want the spline to be non-negative. For instance, if it describes the number of hits on a web server, it cannot be a negative function. So either there is nothing or there is something positive, but it can't be negative. So we have a constraint on our optimization problem where we minimize that sum subject to equality constraint. The constraint is that the polynomial, the function, the spline as a function should be non-negative. And there is a simpler way how to do that, and there is a difficult way how to guarantee that. The simpler way is just to consider a B-spline and consider all coefficients of the B-spline to be non-negative, just a constraint on the polynomials. But it was shown a long time ago that if you do that, then you lose the good approximation property of splines. Then instead of HK order, you get just H2 order, if you just consider that the coefficients of the spline are non-negative. So we don't want to do that. We really want to constrain the spline as such, the polynomial, to be non-negative. And there is a way how to do that, and Nesterov showed it in 2000 in his paper, where he showed that a polynomial on a given interval is non-negative if and only if there are two symmetric matrices which are positive semidefinite and which satisfy those equalities. Basically, that's the relation between the coefficients of the polynomial and the elements of that matrix. So there is some specific relation. The matrix should be positive semidefinite. Okay, then we can take this set of conditions on each sub-interval, and we can define such an optimization problem. So we minimize this quadratic function. Again, we want to get the spline as close as possible to the measured points, subject to 1 to 3 equality constraints, which says that it is indeed a spline, and another constraints 4 to 8, which are some equalities, but those are also the matrix inequalities. So that's another way how to get nonlinear SDP. All that, well, no, the matrices are linear, but then we have some nonlinearity here, we have nonlinearity in here. So again, it's a nonlinear SDP, and here is just an example to show that it indeed works as expected. So this is a sort of artificial example. Those are the measured points, the red ones. This is the 0, this is the axis, so we don't want to go below that. And the red points, they don't go below that. But then if I interpolate it by the spline will go to negative numbers. And the error of this approximation is that one. Now if I add the non-negativity constraint, I will get the red spline, which indeed is non-negative. It does not go below 0, and not only in that point, but also here. Here it's even positive. So it's not about the coefficients of the spline, it's really about the spline itself. Of course, the interpolation error or approximation error is worse now because we have this additional constraint. And here's one more example, a bigger example with many more nodes. And again, the blue one is the spline without the non-negativity constraint, and red is the spline with. And this is the zoom on that part of the figure. You see that the blue goes slightly below, the red does not, as it should be. Okay, that's the end of this example. And let's go to the final example. When should I finish? At 12. I will finish sooner. Okay, the final example is, many of you probably know it, but I just want to, let's say, give slightly different interpretation to the way how to solve that problem. It's the sensor network localization problem. Let me define it using this example. What is given is a number of points, sensors, in the plane. It can be in higher dimension, but okay, here we are in the plane. And there are some anchors here, which are, in this example, they are at the corner points of this square. We do know the positions of the anchors, but we don't know the positions of these sensors. So that's what we want to find. So we do know the position of the anchors, and we do know the distance between some of the sensors, some of the nodes, but only those which are, say, close enough. I do know the distance between these two, but I don't know the distance between these two. So the blue lines, those are the known distances, but I don't know what is the distance there because they are too far. They can't communicate. The signal is too weak. So it's a completion problem. I know I have some partial information about the distances. I want to find all the distances, or in other words, I want to find the positions of all these sensors, which is the same like finding all the distances. So here it's again the definition. So I know the anchors, it's the known location. I have m points, let's call them xi. They have the unknown location. Xi is actually the position of the, so it's the variable, it's the coordinates of that sensor, which I don't know. And what I do know is the distance between xi and xj for certain I and j's, not for all of them, but just for some of them from some index set. I also know the distance between anchor and those nodes which are close to the anchor. So again, the distance of ak and xj only for some subset of k and j. So this is given, that set of distances, and I want to find xi. So it's a simple problem, a feasibility problem with these two equalities. I want to find xi, xj, such that this is satisfied for all ij, and that is satisfied for all kj. There are surprisingly many applications of that problem. among others, it can be formulated as a matrix completion problem. And okay, here you can see just some of them. Military, each soldier in the battlefield gets a sensor, and the general wants to know the positions of all the soldiers. Okay, it can be easily formulated as a least square problem because I want, well, it's a feasibility problem, but so I want to find the minimum of that difference and that difference, or I can put square here instead of the absolute value. The minimum should be 0 because I want to find the exact location. But clearly it's a highly non-convex problem, and I need to find the global minimum. And even if I know that it's 0, it's kind of hopeless to solve that problem. So we can try to approximate it, and how else than by SDP relaxations. And it was shown, well, already 10 years ago almost by Patrick Biswas and Yin Yu that first, that it can be formulated as an SDP problem with a rank condition. How it's that done? Well, easily I just define a matrix, a rectangular matrix, capital X, which such that I put all the coordinates. So x1 is a vector with 2 or 3 coordinates, x2 is another vector. So I will get a narrow rectangular matrix of unknowns. And clearly the square of the norm, xi minus xj, is the same like x transpose x, that matrix, times ei minus ej from the left, multiplied from the left and from the right. And the same for the anchors, the distance of the anchor to the variables. Okay, so the problem then becomes, okay, those are my distances. They should be equal to the known distances. The same for the distances from the anchor. They should be equal to the known distances. And here, this capital Y, that's nothing else than x transpose times x. Now, okay, the relaxation comes in here, that instead of saying that y is the same like, or that x transpose x is named y, I will say that y is a new variable and it's just greater or equal than x transpose x in the sense of positive semi-definiteness. And this is then equivalent to this linear matrix inequality, saying that okay, yet another variable z should be positive semi-definite. So the whole feasibility problem can be rewritten, or actually its relaxation can be rewritten as that. Those are my two conditions on the distances. The matrix Z should be positive semi-definite, so that's the relaxation of that part. And I know part of that of the matrix Z because it comes from the anchors. So this is something which is called, and it's a linear SDP. There is no non-linearity in here. So that's something which they called, this was yeah, full SDP relaxation. And actually it can be shown that it's a pretty good relaxation of the problem. Now, I can write it equivalently as a nonlinear SDP. Just like the feasibility problem, the original feasibility problem on the nonlinear, non-convex equalities can be written as an optimization problem with zero optimal solution. I can take the same objective function. Again, it's just the distance, so that's just the difference between the measured given distance and my distance, and the same for the anchors. So I want to drive this to 0, subject to these constraints, so the relaxed constraint, and I know just a part of that Z. So that's just equivalent to the other problem, but now it's not a linear SDP, it's a nonlinear SDP because we have the square here of Okay, it turns out that this problem is still too big to solve. If you want to solve large dimensional problem, still the matrix inequalities would be too large. So there were a couple of proposals how to still reduce the size of the problem. Just some names of people who proposed some improvements. Actually, I think the best method was proposed by Henry Volkowitz and Matt Crislock, student. But in the rest of the talk, I will consider something which is called edge-based relaxation, and there is a simple idea how to replace this big matrix inequality constraint. Then why is that big? Those are rectangular matrices which are narrow and very long. So the number of sensors is one dimension, and we may have thousands of these sensors. The other dimension is small. So the idea is to replace that big matrix inequality by many small matrix inequalities. Those are just 4 by 4 matrices. So I just take submatrices from that big matrix, only those with indices with the known distances. So that's sort of heuristics, why just those matrices, not other. There is no equivalence that if all those submatrices are positive semidefinite, then also the original matrix is positive semidefinite. So these things are not equivalent. It's another relaxation of that relaxation. But again, it's a good, it turns out that it's a good relaxation. And what did we do? We replaced one big matrix inequality by many small matrix inequalities. So you may ask, did we gain something? Yes, we did, because most of the SDP codes, both Pennon and all the interior point codes, they like much more many small inequalities than one big inequality. So for the numerical solution, it's a good step. Now, okay, so it is a relaxation. So once we get some solution, we may expect it to be just an approximate solution. And typically what you would do, so you still want to solve the original problem, which is, let's say, this problem, where you know the solution is equal to, the objective function is equal to 0. Now from the relaxation, you get very good starting point. You get an approximate solution. So what most people do, they use gradient method to solve this problem from that starting point obtained from the relaxation. My question is, why not to use Newton method? So that's something I don't really understand, why everybody is using steepest descent. We used Newton method, and you will see the result. You basically get the solution immediately. Where are we? And okay, if we use Newton method, then I can say, okay, I will solve the this global optimization problem. I will solve it by Pennon with a very good starting point. And because we only have equality constraints, or only that simple function, Pennon is nothing else than just Newton method. You don't have any constraints there. The other thing I wanted to address is that the typical measure of quality of the solution is something which is called root mean square distance, which is basically L2 norm of the solution. So those are the exact position, those are the computed position, and that's just a weighted L2 norm of the distance. I don't think that says much. Typically L2 norm, if you measure error with L2 norm, you don't get much information. Usually you want to use infinity norm. Why? Because if you use this RMSD, you will get exactly the same number for these two situations, that most sensors are exactly located and just two of them are completely off. You will get the same number as if all the sensors are well approximated, but they are all slightly off. And it may be that this solution is actually much better for your application. You just miss two soldiers in the battle. but all of the rest is well located. Then that where everything is fuzzy. So you know they are basically somewhere there, but you don't know exactly where they are. So we propose just another measure of the quality of the solution, just how many sensors are out of some circle, the circle around the exact location. And it's, let's say, we have two measures. One is a small circle, one is slightly bigger circle. Okay, now in this, in the previous formulation, everything was well defined. So we knew exactly the distances between some of the sensors, and so we know that the solution of the problem, of that least square problem, is exactly 0, because I identified exactly the positions of the sensors. That means I will get exact distances. Now imagine that typically the data are noisy. So the distances, not the positions, but the distances are not exact. This may, so for instance, they are given with some noise here, some epsilon noise, and the same the distances from the anchors. Now we are in trouble because the problem may become infeasible. If the distances are not exact, then you can imagine that there are no points which would exactly satisfy the problem with the fuzzy, with the perturbed distances. So it turns out that some of the methods which were proposed for the original problem with the exact distances may not work at all for the noisy data if you are unlucky and the problem is infeasible. And that's, for instance, the case of this Case-Loken-Wolkowitz method, which is extremely fast. It's based on the graph theory. It's not SDP, which is extremely fast for the exact data, but it's lost here. It crashes because there is no feasible solution, and it relies on the existence of the feasible solution. But with the SDP relaxations, that's not such a big problem. With the linear formulation, and that's already the approximation, what we do, so instead of the original equalities which were there, originally this was known exactly, so we had the equality that our distance, the computed distance, should be equal to that. Now we have to add, we know that this is not exact, so we have to add some noise here, or some let's say, slack variables here, u and v, and we just try to minimize the sum of all these additional these slack variables. So it still can be formulated as a linear SDP, but I claim that it's it's better to formulate it as a quadratic SDP, because that's my original quadratic formulation. I minimize the difference between the given distances and the computed distances subject to the SDP constraints. And okay, if these are exact or not, I don't care. So if they are exact, I know that the solution should be 0. If they are not exact, the solution, the minimum, will be something else than 0. But okay, the formulation of the problem is exactly the same. So the claim is, which is, let's say, supported by numerical evidence, by nothing else than this quadratic, that it's better to solve the quadratic SDP than the linear SDP, that you will get better results faster. So that's the motivation for nonlinear SDP formulation. And let me finish with one example, which was actually Y65, that was created for Claude Le Maréchal's birthday conference. Okay, that's those are the unknown position of the sensors, and the blue are the known distances, and you see black are the anchors. We have 9 anchors here, and the red are the distances to the anchors. And again, you see that, for instance, the radius of the known distances is not big. We don't know the distance between that point and that point, for instance, or between that one and that one. Okay. Now, these are the results obtained, and okay, those are, this is a problem with exact data. There is no noise in this one. So these are the results obtained by the linear SDP formation, which is obtained by the nonlinear SDP, which actually we have linear matrix inequality but nonlinear objective function. Is there any difference between those two? Well, this one seems to be slightly better. You see, or sorry, I forgot to say, these red nodes, those are the original positions. That's what we want to find. The blue ones, those are the computed ones. So that's my solution. And you see there is bigger error in here. Those are the computed ones than in here. Here, those were located exactly. Again, there is slightly smaller error here than in here. If I compute the L2 norm of the difference, I will get more or less the same number. But if I compute those which are out of certain radius, then I will see that the quadratic formulation is better than that one. 300 nodes are out of the small ball, 350 are out of the small ball for the linear formation. The same here for the larger ball. But where the difference is even more significant, now I take that solution as an initial solution for the Newton method, just apply Canon, which is just the Newton method, and what we get is that one. Okay, it may be pure coincidence because you never know. So if the initial solution is good or bad to find a global minimum, but okay, in this case it worked. Here the initial solution was good enough to locate all the nodes exactly, while here the solution, the initial solution coming from linear relaxation was not good enough and many of the nodes were not located. Actually, the solution is worse than the solution from the relaxation. The Newton method went to the wrong direction. And you see here the corresponding numbers. Newton from the linear starting point gets you worse number here, better numbers here because more nodes are identified, but some of them are really way off. While if we take the solution of the quadratic SDP as an initial point for the Newton method, we have that exact solution, and that's it. Thank you.
Well, there's still plenty of time for questions.
For this example of sensor network localization problem, you have a number of solvers, and the interesting thing is that looks like everybody test the solvers using examples like this. But for example, they are molecular conformation protein data bank examples. Why don't those people test the solvers on those real data?
Because they are lazy.
So this is the artificial. For example, you put the sensors at the four corners, then you generate random sensors over this unique disk. Then probably
let me disagree a little bit.
Yeah.
The typical example is example of that type. I don't have the final example, but you have random sensors in a unit square.
Yes.
And I agree that those are bad examples because, okay, those are not real world examples. I don't think, well, this is different. I don't have random sensors everywhere. I have random sensors along some lines. You can think those are motorways, for instance, and those are cars on the motorways. So I think that this is a more realistic example than randomly everywhere in the square or in a circle. But okay, it is still an random academic example. So I didn't compute this micro. But let me just say that this kind of problems is actually much more difficult than if you have randomly everything everywhere. Because, okay, it's much more tricky to identify a circle nodes which are almost on the circle, just slightly away, then nodes which are, let's say, randomly but regularly, kind of regularly distributed. So many codes would crash on that example. The crystal code would not solve it.
Have you tested your panel solver against those protein data bank examples? They are publicly available, easy to download.
No. The answer is I said that people are lazy. I'm lazy. I didn't do that because I didn't have time. So I still would have to write down some interface.
Another question, probably you can comment on. If, for example, I place the sensors over a sphere, would your formulations still valid for that? Because the sensors, you need a radius, but you don't know the center of the ball. But you want to put the sensors over the ball, over the sphere, and also you want to keep the distance among some distance among some sensors. So would all the formulations still adequate in dealing with that case?
So in other words, there would be no anchors. I tried it once. I think it would still work.
My question goes in exactly the same direction. So what I tried is like packing problems. So you don't have anchors, and you don't have an approximate distance, but you have a minimal distance. Maybe I used another formulation. I don't know. I did not compare the models, but STP was, at least in my model, which was probably bad, was very, very bad.
Yeah.
It performed very bad. Do you have an explanation, or is just my model?
Well, the explanation is simple because the solution is non-unique. So, and you want to find the locations, coordinates. But okay, every shift is a feasible solution. It can go to plus infinity to minus infinity.
Okay, so but when I added some constraints saying that this object should be, so I had a rectangle. I say this object should be in the left upper corner, the other should be here and there. So I think I added constraints so that there should be some unicity, and still it was very bad. Still, but maybe.
Okay, I didn't try that.
Maybe my model was really bad.
Maybe that, yeah. That one has to be clever with these additional constraints. Sometimes simple bounds are not good additional constraints. So
okay.
It's better to put some norm of something.
I think there's a paper by Kurt Landstreicher where he adds some very clever symmetry breaking constraints to circle packing problems, and it helps quite a lot.
Okay.
With problem, did you use intervals to describe to constrain the distance, or is it exact?
Sorry.
For this problem of sensors, so do you consider also intervals for the distance?
No.
Maybe if there's no further question, I have one. So regarding this approach that you described for the control problems, if you go for larger ones, does this formulation into polynomials still work in a reasonable way, or will it be too dangerous because you get too high degree polynomials?
What is larger? So you can have either large dimension
Depends on the control
or high degree.
If you need
So
more.
if you go to a higher degree, then you would get into numerical troubles probably. If you go to a higher dimension with reasonable degree up to 5, actually the main work was done in translating and finding these matrices H, not in solving the
If there are no further questions, then let's thank Michal again.